thinking about Jacob, and I felt like there was something I was going to
talk.
say to him.
Say to him
or
something. Yeah.
But I don't know what that would be. So.
No worries. It'll come out later on the story.
Chapter 3, 2. Chapter 4, 2. Who is next Wednesday?
Free radical part of the homework too? Or is it?
Yes.
Okay,
Homework
so,
three?
so the free particle is not part of the assigned homework, it's just talking
No,
about
that's just a summary we discussed last time, right? I just want to make summary, a brief summary, remind you what we discussed and then also discuss the new type of potential.
Can you see? Figured you'll see it here.
Yeah.
Thanks, Mr. Roger.
that is about the property of free particle we discussed last time. And I just want to summarize since we have several concepts here. Then we are going to change to another system or another type of potential. So when we say free particle, potential zero, no potential, right? So the particle can freely move in the whole space anywhere, no any scattering or attract to some wheel, so there's no. Then because the potential zero, so we have the Hamiltonian is only the kinetic energy, we solve the Schrödinger equation. Wait a moment, I think I did something. It's the Schrödinger equation. When we solve this Schrödinger equation, we have the solution for energy. Since the K, there's no restriction on K, any value, then that is a continuous spectrum that energy, any energy is possible. No any forbidden energy, and then the solution mathematically, right? It is math. Mathematically, when we solve this second-order differential equation, we got this one. The solution is a plus minus exponential ik. We know that's a period. So based on this, suppose it is acceptable, a physical acceptable function, then we can build up with a stationary state, right? Stationary state. At any time, any position to describe the free particles physics, spatial part and the time dependent part. However, what we found this solution mathematically acceptable but physically unacceptable because in this case, for given K, right, energy is well defined and momentum is well defined. So we have well defined states. That means the fluctuation for the momentum is zero. Then according to the uncertainty principle, to describe where the particle is, that is go to infinite, right? And that is physically unacceptable because we know the free particle must be located somewhere, right? So this is not correct if we accept this function. Then let's look at the total probability. We also found this one go to infinite. So it does not mean, physically we need to know that either equal to 1 or normalized, or at least the finite. So this is not accepted. Third is that if this wave characterizes the propagate or the movement of free particle, this velocity of this propagational wave gives us this number, but it's not equal to, if we define that is the moment or speed of the free particle speed, momentum divided mass, so they are not equal. So because that means this is not the well-defined or physically acceptable wave function to characterize free particle. So how to solve this? Then we will say that the free particle actually is superposition or linear combination of all the K. So that is the wave packet. Right? The wave function be physically acceptable because like this means we have the weighting factor for K, then sum of all the K possible together. That means linear combination of all the plane waves together, right? And this is the weighting factor. And how to determine the weighting factor? Oh, I didn't, I think, if you remember, right? So that is, okay, initial state. That is also the Fourier transform of this. Minus infinite and exponential minus ikx and initial states to the integral is OX. So that means initial states of this free particle determine how this the weighting factor of this K give us. Then you have controlled by this, you will form this different type of this wave packet. So if we say that is the wave function of the free particle, then we found, yes, this is finite. Since this is a combination of all the possible K, the momentum. Then it follows the certain principles, we can also give us the localized or at least a certain range of this probability to find particle. Normalization over this total probability is finite of 1, that is physically acceptable. And we also derive that this group speed will be determined, right? That is nothing but the speed of the free particle. So yes, they solve this one, these three problems, so, okay. The real physically acceptable wave function for the free particle is wave packet, not the plane wave. Okay, today we discuss another type of potential. Here is 0, right? So now let's consider potential step. If we have this type of a potential, so potential step, let's first, V function is 0 when x is below or negative, and a certain number of V naught when x larger than 0. So if graphically, it's like here. This is V, and we have V naught here, so 0, x, right? That is the potential, so we call it step. Means below this negative axis, all still like free particle. Then suddenly at the 0 K, this position, the potential sharply increase with a step and then keep a constant. So now, in this potential, we are going to discuss what kind of behavior of the particle. Okay, so that is the, now we have two regions, so that's region 1, region 2. Because the potential difference, so we must solve the Schrödinger equation, we have to also separate in two regions, right? So that is the case. Okay, now the Hamiltonian, okay, so now Hamiltonian is the kinetic energy part plus potential, right? And that's equal to also separate the two regime. This first region potential is 0, so still here only the kinetic energy. X. And the second region, we have a potential step. Then keep this in mind. So in general, we are going to solve the Schrödinger equation, right? Schrödinger equation also separated into two halves. First, in the region negative, only this kinetic energy. So now we are going to set function separate. So region 1, I'm going to set 1, Ex squared, that equal to E set 1x, right? For this region. And the region 2, we have a potential. So we have both the kinetic energy. Now I'm going to use psi 2 to say that wave function satisfied that equation in the region 2. Plus Vx, okay, Vx is V naught, right? So we just direct this. It's V naught, psi 2, x equal to E, psi 2, x larger than positive. Okay, now the solution. Solutions in region 1 and region 2 also depend, right? So solutions, it will depend, we are going to discuss separately. Depends on the E, initial energy, right? So if the initial energy is higher than this V naught, another is lower, right? So there are two cases. So we are going to discuss separately, since they will give us different solution. Now let's discuss a case of energy is higher than the energy step. Okay. Let's consider this case. If higher, so what's let's classically, right? So consider classically what kind of solution. Classically, what kind of motion of the particle, and then consider, then we are going to discuss quantum mechanics. So classically, so particle energy is higher than this, then what happens? it will free move, right? In this region, free, and then come to here, since we have a potential like scattering. So it kind of weaken this motion, but still keep going, right? So that's like a scattering. And let me see, no reflection in region 1, region 2. Sorry, region 1. And so this is totally okay. So even though there's an energy like an energy barrier, but if the energy is higher than energy barrier, we know it still keep continuing. That means if it come to here, it will not go back, right? No reflection, not classically. Just the energy, since the barriers will have a clamp up to the energy barrier, but still can keep going. So that is classically. Then how about the quantum mechanics? That, to answer this, we have to go to here. Solve the Schrodinger equation, right? So that is the key, so that we are going to answer this question, and you will see in this case, in quantum mechanics, there still has a possibility to reflect and, of course, keep continuing. So in this case, right? So now let's do that. Solution, right? So now let's go to, since this solution, let's see. Solution in region 1, that's region 1. We know this one, we can divide these numbers both sides, so we have the, just write down this mathematically, the second derivative, which is plus k1 square of f1 x equal to 0. k1 square we define it is 2me over h bar square. Right, so I just divided this term and then move that term to the left-hand side. Okay, region 2. Sorry. Region 2, we have K2 square. Here, K2 square is 2m e minus v naught over h bar square. So you see the formula or the differential equation is the same. Only difference is the constant difference. Then the solution, right? So solution we have the first region. The solution is sinusoidal, right? And the sinusoidal we can have the, if you consider like this, we will have plus minus. So we are going to put together linear combination of plus and minus. So like the data coefficient A, and this one is going to be positive x plus b. So that is for x smaller than 0 or smaller equal to 0, right? So 2, region 2, similar things. Now the coefficient we are going to use different, since a different region. C, E, I, K2, x plus E, E minus I, K2, x. This is the C. Okay, so let's first discuss this behavior of this, right? So this, you see, this positive means that if that is like propagation to the, this is to the move or propagate, move to the right direction, right? And E and D, this negative, so that move to the left. So what does mean? There are two, okay, let me just use this figure. Okay. So in this region 1, we have a combination of two waves. One is propagate to the right, another propagate to the left. One is, if we say this incident, another is reflect, right? And in this region, we have also C, E, I, K2x, and the B is to the left, minus I, K2x. So totally we have a full wave or plane wave that propagate in this whole space in this case. Now, we are interested in see what happens. So, what we are interested, we want to see if there's a particle move from the left, move to the right direction. What happens when they hit this stack potential? What kind of motion will change? It's will complete like the classical complete transmit or partially reflect. So now this is our interesting. Is what? Is how the particle moves from left to right. So what we are interested in is, suppose we have a particle from the left, then try to move to this direction. What happens at this position? It will keep like classically 100% transmit, no any reflection, or there are partial reflect, partially transmit. That is our question answer. So if we consider this means initially, this one is instant particle or wave, right? Instant. This is reflect. And this one is transmit. So this one is not we are interested, right? It is this one like a particle from right to move to the left. So if we consider this, we just consider what happens if a particle from left to the right. If we use interest from right to the left, you just select this one, and this one, not it, right? So that is just, but we just consider when we have a free particle move, and then when we hit, there is energy barrier will not happen, right? So that is what the interest. Then we remove this one. We are going to remove this. So the question is, how about the reflection and transmission? Oh, transmission, sorry, transmission. Not at region 1 and 2. Right, so that's the very interest. Okay, so then the total wave function, when we say yes, in time, this is the total wave function speed, depending on which region, right? So now we are going to rewrite here. The first region is spatial part is step 1, multiply exponential time dependent minus I, if we use omega here, okay, and it's omega 1t. Which is A, is this one, is this part, A exponential I, k1x minus omega 1t plus reflection B, because in the same region, right? B A I minus I k1x plus omega 1t. Here it is x, and now give you what is omega 1 and what okay, so that is side 2x minus I and 2t, which is a C E I K 2x minus omega 2t, which is going to be positive. So here, omega 1 is just this E1 over T, right? That is E1, you know, that is E1 over H bar, which is H bar K1 squared over 2m. And omega 2 is just E, because okay, E1, this is in this region, so we have K1 2 over H1, and that is H bar K2 squared over 2m. So here E1 is E in region 1, and E2 is E minus omega 1. That is, we defined the cake, right? Okay, so with this, now you can see we already dropped this, this thing. We just consider this. In region 1, we have a combination of incident, reflect, and region 2 only transmit. So here, I'm going to give a definition. So here, this part, A exponential I K1x minus omega 1t, this we call the incident wave. Function, right? And B exponential minus I K1x plus omega 1t. This is reflection, or reflected. Then the C exponential I K2x minus omega 2t. That is in region 2, which is transmitted twice E. Okay. Here, this is A in the region, so then the third one transmitted is this. So now we can give this behavior of each grid. Then we are going to discuss, before discuss this transition efficient, we look at this probability. So what is the probability of finding the particle in region 1, in region 2, right? So now we are going to see the probability is psi xt squared, right? Depend on time and also depend on the position. So we just take square. Then this one is also, because we have two regions, so we have also two parts. The region 1 should be, okay, should be that one. A exponential I K1x minus omega 1t plus B exponential minus I K1x plus omega 1t squared. Absolute, right? That is probability means psi star multiplies itself. So that because we have two terms, and these are all complex, so be careful here. And then if we extended this one, you will see it is several terms. Multi of A square, B square, and plus cross products, right? So cross products, A star B exponential. Since you see this is omega 1, and this one, this negative, I mean, if we take this amount to this one disappear. Only the difference is this two, right? When we multiply, so that you have minus 2I K1x, another cross product A, B star, exponential positive 2I K1x. Since omega 1t, I omega 1t, that is equal to 1, right? Magic, so that is this. Then you see here, we have a constant. Then we have, if this put together is like a sinusoidal function, right? Then the region 2 is a C exponential I K2x minus omega 2t squared. And then you see here, this one is the phase factor. So its magnitude is 1, right? So that is nothing but C squared. and what it looks like. So you can plot the probability in this space, in this region 1, region 2. No. Just follow this. Okay, let me see. Keep here. As a function of x, right? So this part is like sinusoidal function. Because here we have the term, well, a negative plus, so that there's a constructive. So here it is like constructive part. The instant wave and the reflected wave, they construct each other. So there's a peak. Then this one is this term. So in the region 1, because we have two waves, these two waves depend on their phase, incident and reflect. So the some position they constructive, and some position destructive. That is behavior of probability. You will see that is like still like sinusoidal function, but in region 2, since it's a constant, so the probability to find particle is constant. Yeah, right? That is the behavior of the probability. When we find we have this. Now we go to see this transition. Now we are going to evaluate the reflection and coefficient. We're going to discuss this. As first, the definition, reflection coefficient means if we have the ratio is reflected.
Dr. Yu,
Yes,
I have a question.
yes.
How can the probability density have an imaginary number in it?
Or you can, okay. So you can take this absolute value, that's fine. Let's see. When we do this, this is the imaginary part multiply its real part. I mean, complex conjugate part, right? So it's here, the complex conjugate, we have star, we have minus. This takes star, this takes minus, right?
Right.
And this one also takes star. So we have a cross term. That cross term comes to here. So this one in principle give us the positive one, I think. I mean the value. Or in order to make more safe, you can make this absolute value. If there's a negative, there's an imaginary, make this absolute value. Let's see, I think this, yeah, this is a K. Here we have imagine, so this is a, still we have an I here. We cannot ignore the I. So I is still here. So that is why we have a sinusoidal function here. If it's not I, this is like a decay, right? So that to make sure that it is be absolute or positive value, then let's take the this one. I think if we do not do this one, since this two will control that, so this one, of course, still we need to make this one unreal, not imaginary or complex. Yes. So. Of course, if we know this coefficient are same, then definitely it is real, right?
Right.
So, yeah, maybe let keep in mind maybe you just if we have an imaginary, we have to take the absolute value of this part. But the absolute value is be total since we have a negative sign here. So I'm going to say that to be safe, you still keep absolute value after that. But this one, you have a negative, you have sinusoidal function, sine, cosine here, and then if this is imaginary, so you still take this, if this is a sum of complex numbers, you take the absolute value, you still follow that absolute value with the heat. Let's see here, reflected current density divided by incident, right? That is definition how much reflect with the total incident current density. So that is, remember we end of chapter 3 we introduced the current density is G. If we use reflected, and then G incident. That is, we are going to estimate how much they reflect or percentage of reflect when we have an incident. So similarly, for the transition is how much transmitted current density divided by the incident. So that is G transmitted divided by G incident. That is how we analyze. And then now the next job is how to calculate this current density. That current density as defined, if you remember the definition of this, so we can easily, since we know the wave function, right, so we can calculate this. Let's do this. Because the definition of G is I H bar over 2m, and inside is the wave function and multiply its first order derivative of its complex conjugate, x minus its complex conjugate multiply the derivative of the wave function itself. Right, that is definition in chapter 3, equation 383. So because this, so the G incident is IH bar 2m now inside. So incident here. This is incident curve, right? This wave incident, reflect, and transmitted. So you just substitute this one into different. Now here we have I didn't give a name, so if we put it into that, okay. Then before this, so let's do this. So for incident, the psi, you have psi, if you want to have index of the incident, is A I K1 x minus omega t, right? And then we are going to do this derivative since we need a derivative. Incident x. We do with respect to x, so we have I K1 x. This I K1, right? Then multiply itself. Then you also do this, we have a complex conjugate, so let me just do this one first, and the remaining part, for others the same, so I will skip the intermediate step. This one you just take complex conjugate A, takes complex conjugate, and this one becomes minus, right? K1x minus 1. Then the derivative of this one, incident, xt dx is here, we have minus I k1 a star exponential I k1 x minus omega t. Wait a moment, I think, yeah, derivative just, wait a moment. Yes, yeah, this key is right, just do the derivative. So when we have this 4, we sub into here, now this incident current density is just sub it into here. So I skip that one, I give you the final result, which is h bar k1. Some terms cancelled in school. And this formula is just substitute these 4 terms into this equation here, then you can find, you get this. So similarly, let's look this for reflection. Reflect. Okay. We have also 4 functions. So we function reflect is b, right? B exponential minus I k1x minus omega 1t. Plus, right? Because this go to the left direction, right? So then this d, sorry, okay, dx, we just have minus I k1, b exponential minus I k1x plus omega 1t. And do the same thing for the constant conjugate. B star exponential positive I k1x plus omega 1t. And this derivative dx is I k1 b star exponential I k1x plus omega 1t. Okay. So each term you have to do carefully. Then let me give you the final result of this current density for the reflected is equal to minus h bar k1 over 2m b squared. C for its transmission trans E here we have trans, just simple trans, okay. Xt is c exponential I k2, right? X minus omega 2t. E sine trans dx I k2 c exponential I k2x minus omega 2t. Here, so the star is trans is c star exponential minus I k2x minus omega 2t, and b trans dx is minus I k2 c exponential potential minus 5 equals x minus 2. Okay. Now I think this is. Now finally, we also have this current density for transmitted is h bar k2, k2, 2m, and c squared. All right, now we can answer these two questions. Since this 2 is nothing but the ratio of this current density reflect to the instant or transmitted to the instant, right? So we can easily substitute this. So now let's first look R. R is J reflected to J incident. And that is incident. So you see the coefficient, reflect coefficient here the same, right? H bar K 1 over 2m, and we take absolute value, so the minus sign disappears. Only the ratio of B and A, right? Only this coefficient. And of course, how much the coefficient is, we are going to do. Let's first give the formula, then we are going to go to next step. Then transmission is J transmitted divided by the absolute value of J incident. Now here, this is different. This is K1, K2. That is K1, right? So we have a ratio. We have K. The denominator. This is a K2 in the numerator, right? Denominator K1. And C squared over C squared. Very simple. If we know the coefficient A, B, C, right? So next job is try to find what is A, B, C. If we know, we can estimate or evaluate how much reflected, how much will transmitted, and we'll compare with classical. So now, the next job, A, B, C. How to do this?
Boundary conditions?
Boundary condition. We haven't used boundary condition so far, yes. So that's from boundary conditions. Now, how many boundary conditions?
3.
First, yes, how many?
3.
3? Okay, let's do. First one is we know, let me use erase, right? I have a region 1, right? So actually, boundary condition space, so ignore the time dependent part, just the spatial part. Say 1, x equal to 0 should be equal to 2x equal to 0, right? Is this position here, the wave at this position should be same, right? So that is 1. If you, okay, let me just, that is 1. And second one, you say you have 3, 0. Second one, which one?
When you go to x equals infinity,
Go to infinite?
it would equal psi 2.
Yeah, but that is, if you go to infinite, you know that is just psi 2 equal to, it will go to 0 whatever, but not the connection between these two. So we only have this, only one boundary.
Okay.
Then, this is not enough. We have how many? At least we have 3 unknown variables. We at least need 2, right? So if 2, we cannot solve 3, but we can find the relation between 3. Second one, yes.
I thought part of the reason why we ended up with the size that we did of the wave package was because we had to have it decay to 0 at negative infinity and infinity.
You're right. That is, we should consider that. That is in more related, but we just focus on a given wave. This is just focus on for given wave what kind. If wave packet is for the combination of all waves propagate to this one, right? Yes, you're right. That's to characterize the free particle, we need a wave packet. Here, we just focus on consider if this given 1K, what kind of reflection and the transmission. Then, if we really want to describe the particle, we have for each one we have a combination, inner combination altogether. So this is just one, for given 1k, what will happen? Okay, second one is, remember, this momentum, right? Wave functions will continue, momentums will also continue, right? So for this is a wave function. Because we know the wave function characterizes the particle or conservation of particle cannot suddenly created or discrete. But another is the momentum. Momentum continue at this, and then what is momentum? Remember, momentum is p, right? Is I minus IH bar dx. That is in region 1, right? So p. Let me just as x equal to 0. So equal to the momentum at the right hand side. Right, this is the momentum operator, remember? Momentum operator P minus IH bar dx. So that is give us the momentum should be also continued at this side. Then this momentum operator apply these functions be also in region 1 be also equal to in region 2 at this boundary condition. So we need two conditions. At least we have two equations physically, right? That is physically required. Okay, so now let's set up this. So we have the condition here. This one, did I remove? If you remember, we have incident and reflect, right? We have two waves together. So we have a exponential I k1 now multiply 0, x equal to 0, right? Plus b exponential minus I k1 multiply 0 equal to c exponential I k2 multiply 0, right? That is first one. And then you do the derivative. Since minus I bar cancel, right? So actually only is this part equal to this part. So next time you don't need this I bar. You just consider the boundary condition. One is the wave function is continuous and its first order derivative also continuous. Okay, so now first order derivative you have this one is I k1 and then a exponential I k x and this is minus I k1 e exponential minus I k1 multiplied 0 equal to here I k2, right? C exponential I k2 multiplied 0. So this you just simply is a plus b equal to c, and I cancel, right? The k1 a minus b equal to k2 c. So the remaining part is max, right? For example, you multiply k2 both sides, then you have minus that, no, okay. Then you have this subtract each other, so this term is 0, and this one is disappeared, become b, right? So remaining is b, and this part I think I already have now. So now let me give you a very easy, if I say this is equation 1, equation 2, then this k, k2 multiply 1, and plus, or subtract, equation 2, you have this b equal to k1 minus k2 a over k1 plus k2. So we have this. Then we have a b. You just we say this equation 3 and make the 3 sum to 3 to 2. So here, or actually we have b, right? So from here you sub the B here, then you can see find C relation with C and A, right? Then we have a C is 2K1 plus K2 over A. So now we have the coefficient. Now the A and B as function of A, B and C function A. So then we substitute this into 3 and 4 to R. R is B square over A square, right? And you just use this one, so you can see very simply it is 1 minus, K1 minus K2, K1 minus K2 square, and the denominator is K1 plus K2 square. Now I'm going to replace by kappa, and I'm going to give a capital K, give a name. Capital K here is defined as a ratio of K2 over K1. Then similarly T is K2 over K1, C over A, right? Then we will use this relation here so you can see that is 4 K2 over K1 here, and this is the 4 here. Then we have 4 K1 square, and the denominator K1 plus K2 square. And that is 4 capital K 1 plus K square. Okay, K here, K, capital K here. Ratio K2 to K. Remember K2 is square root 2 M E minus A naught over H bar, and this is 2ME over H bar, right? So H bar cancelled, and the 2M cancelled, then that is only one of square root this ratio. And that's be smaller or equal to 1, since this one is positive, right? Depend on E naught. So you can see, even though energy is positive, larger than the V naught, but depend on how close to V naught, how far with V naught. Then this one, it will change. If this one change, you will see this reflection and the transmission will also change. Now we can discuss. So you can see here, the reflection is not 0. Classically, we know it will totally or 100% transmit, will not or no reflection. But quantum mechanics, we found there's a possibility that the particle reflect. So now we discuss. First one, okay. You can also double check this one equal to 1. That is very easy. You just add these two together, and you expand this one. You will see that that equal to 1. You can check. Second one, this that is a conservation. Make the conservation of particle, right? Particle either reflect and transmit this probability add together to be 1. Now this one R is non-zero. Okay. So that means there's a non-zero. There is a reflection. Reflection. And this is a pure quantum mechanics, since it is classical. I cannot explain this phenomenon. And this is due to the wave behavior. And the wave of particle. Since we characterize this in terms of this wave function, and wave function always propagating into the space. And when we propagate, we know there's a destructive, constructive, so the probability the reflect is possible, is non-zero. And so now third one, that's how much transmit, right? So that one, let's if we write down here, that's really depend on K, right? How much K value. So that if go to 0, when k equals 0, right? When k go to 0, here, when k go to 0, is this one equal to 1? That means energy just equal to here. So right, so that is no transmit, all 100% reflect, right? So that is when energy equal to But if energy is much higher, so this value is almost go to 0, then the transmission is 1, right? That is when it's close to 1, the energy is much larger than this. So from this situation, you can see the quantum mechanics. Yes, that is indeed different, and the experiment can measure such the probability. And if you find the probability of the reflection, you will prove the quantum mechanics is wave particle duality, right? All right. So now let's consider the case of energy is. So now we consider this case. If energy low Hadley barrier, so classically, what will happen? No transmission, right? It will always totally reflect. Totally reflect. Since the particle has an energy barrier here, and if the energy is lower than this, you have to go back. Right? That is classical. But now we want to know the quantum mechanics. What will happen? We will see. Even in this case, we still can find the probability the particle penetrate inside this. Right? So that is interesting. Now let's do that. Okay, in this case, we again we go to solve the Schrodinger equation. So now here I will not write down Schrodinger equation. So equation here, the region 1. Okay, d squared dx squared plus k1 squared minus, I already observed this dot number into this k, right? K1, so sine 1 x equal to 0. Here k1 is again this n e over h bar for x. And the second one is now minus k2 prime. Here, that's the difference. So k2 prime is square root 2m. Now it's v naught minus e, because e is lower than v naught, right? H bar square. Because we have a like sign, here I change the position, right? V naught minus e, so we have a like sign here. Then you will see these two solutions different, right? This one is still sinusoidal function, and this one is exponential, right? So now, let's see the two solutions in two regions. Mathematically, it's different, right? So now, solution or general solution. In the region 1, that is still the combination of incident light, still same thing here. Incident light, k1x plus b exponential minus I k1x. But region 2 is exponential. Mathematically, we have k2x minus k2 prime x and plus b k2 prime x. Two possibilities, right? All are satisfy this. But now, this exponential has no I, so that is a real number. And now I'm going to ask you, physically, now this is mathematical, right? Mathematically, now physically, when we solve this Schrodinger equation, we always double check whether the solution are acceptable physically. So now, are they acceptable? All this case, the first one we know, yes, it is characterized incident light, wave, and reflection. How about this one? These two terms are acceptable. This one means decay, right?
Mhm.
So when x go to the positive infinite, it's decay to 0. How about this one? Increase.
Mhm.
So that is not accepted. We have to drop this one. Okay. So then when we pop this, and then finally now, physically acceptable wave function, now I'm going to write this way. The first, like I said, region 1, we have an instant light, instant wave, which is still same as before. We have this k1x minus omega 1t and plus reflected minus I k1x plus omega 1t. But the region 2 is only this decay. Okay, minus here. I omega 2t. Here, this part always has I because it's a time-dependent oscillation. This one is a real special part, right? All right, so once we have first select the solution and found physically acceptable is this, then let's first look at the probability. The probability to find particle is the same information not given from the classical or different. The probability is, again, we have this, take this square, right? And same thing here, I just write again. A1x minus omega 1t plus e into minus a1x plus and another is the c exponential minus k2 x plus or minus I omega 2t. Then now this right hand side, same thing. But the left hand side, the region 2 is changed, right? So now if you look back to this curve, so you see here in the decay. That is because, okay, I didn't give you, I think this one, same as before, so that's equal to, again I have a square plus b square plus the term, and this one only c square, but now we have exponential thing. This is real, right? Exponential 2 minus 2k 2 prime x. So the probability now, this is really quantum mechanics. Quantum mechanics behavior because we have the wave decay. So classically, there's no possibility to find particle inside of this region 2 since we have a barrier. If we put 100% reflect, quantum mechanics say no. But this is probability. How about this transmission probability and reflection? We can do the same thing. We can do the same thing. Let's see. This is similar, so I will just give you a result, right? The intermediate do the same thing as we did before. The value 8, the R, and T. So R, okay. And second, T is okay. Now we need again calculate each individual, right? So I just gave you a result. And since the same thing, the procedure is same. You just select the wave function here. This is incident light wave. This is incident wave. This is a reflected. This transmission rate and substitute into the formula. So now let me give you the final. This one doesn't change since this the behavior in the right-hand side is same. So the same as we previously we have this formula here. That's a reflection. Reflected is also the same as before, since that is all in the region 1. We didn't change region 1. But the transmitted since it's a real part, when you substitute to this current density, you will find cancel each other. Yes.
Since the D term here has to go to 0, does that mean that D is 0 for the other case where E is greater than B0?
And the other case, the previous case,
Yeah.
the previous case, we still have this oscillate, that is kind of plane wave, right? That is only the plane wave propagate along to this right-hand direction.
Mm.
So that physically is still acceptable because that term is not infinite go to. So that's fine. But that we drop because we just consider the particle from left to the right. And that component, or that one is characterized from particle from right to the left. But this case is physically is not acceptable. Okay, so here y equal to 0, you can just do yourself, but you can analyze very easily since this one is real. And when you do the derivative, you do that it will not cancel, the exponential part will not change. So you have a negative sign, it will cancel each other. That is very simple, so I just give you. But so then the conclusion is 0, right? And that is something like this classical transmission. The probability over the coefficient is 0, but it does not mean the particle is stopped here 100% reflect. It still can penetrate to certain value and decay unto 0. So that is the quantum mechanics in this case.
Does this essentially physically mean that it just, in quantum mechanics, it takes a little bit for it to be reflected, that there's a cushion amount of time before it can be immediately reflected?
It takes a little bit because the particle is decay here, right? So it takes, the coefficient is one, but you want to really try disappear, so that means then up to this threshold, actually it's totally reflect. So there are some threshold here, and then actually after that still no any possibility to transmit. So in principle, we will say that this reflection still, if you go to see this reflection here, it will go back to the ratios, they are the same. That is from not from this just this case just means classically there's no just from here to reflect, but the quantum mechanics means it will go to inside a certain distance, then totally stop here. And then actually no any further transmission to go to the region after that, so that is 300% go back. So that is this case. But the difference is that does not mean certainly reflect at this position, but they still have a penetrate here. Yes.
Is this tunneling effect?
No, that's not tunneling. You mean tunneling, right? That's I'm going to discuss next one. Tunneling is that we have this finite windows of this stack, and classically we go to here and come back, but the quantum mechanics is that is. Let's see, we have time. Yeah, let's start it. Then we keep continue discuss this. So now we are going to discuss this type of the potential. So far we discussed the step is that after the positive, all the potential go to infinite. But now it's not infinite, it's just finite windows of this energy barrier. Then what will happen? There's any barrier, so that is now we will discuss K. So barrier. depend on the potential is a positive and negative, right? So now let's first consider the barrier. Barrier case. Okay, so now the Vx, now we have three regions. So suppose we select this still 0, but now we have a x. So we still have V naught here. So then you can see here 0 when x negative, yes. But when the V naught is only for some region, and 0 again. So we have a region 1, region 2, region 3. 1, 2, 3. How many boundary conditions? 2, right? The previous one only 1. Now we have 2, and you can imagine that way. At least we have 4 equations. Each 2 for the continuous wave function and 2 for this momentum. So that's the first order derivative. Okay. So now, since the procedure is similar, I just give this a difference. The difference is this one. So now let's first the Schelling equation. Now we have a 3 region Schrödinger equations. The first region is only kinetic energy since potential energy is 0. I'm going to still use psi 1. Go to E psi 1. That is x. And the second region, we have the energy barrier in area. D squared psi 2 x dx squared plus V naught psi 2 x equal to E psi 2 x. And the x is within the 0 and 8. Third one, go back. But is we function is third. So we need to distinguish. Equal to E psi 3, since the area is different. And again, we have to discuss depending on the energy is higher than the energy barrier or lower energy barrier. Let's first discuss higher. The energy lower is this case, turning. That is the next type, right? So, but if energy higher, then what happens? So let's consider. So we have E, 1 is here, 1 is here, right? Now let's consider first case. Case of energy larger than the energy value. The solution, okay, I just write down here. Solution is very easy, similar as we did, but now you can see we have 3 regions. So we have a K1, K2. How about this one? K1 again, right? So this is a K1 because these 2 regions energy is the same. Only potential difference here, right? So K2 here, K1 back here, right? So let me give you the region 1, the wave function is a combination of incident and reflect in region 1. X plus B minus K1x. Then the region 2 is again here. If we have incident and reflect, here we also have an incident reflect because here energy is still. So in this case, since this is finite, we have considered those both. E since this here, even though we consider the instant light particle come to here, partially reflect, partially transmit, and then at the second boundary also has a reflection. So we need to consider this term. But in this in the region 3, we only consider this one. Okay, so the solution is for particle moves from right to right. Let's consider this situation. So here is we have another term is this in the region 3 point to the or move to the right. That is the particle from right to the left. So if we only consider from left to the right, we have incident, reflect at boundary 1, and coming to here, transmission and reflect at boundary 2, and keep continuing reflect. So we have 1, 2, 3, 5, right? Okay, let me stop here, then we go to this class. Similar probability and transmission reflection, what happened in this case. And you will find this resonance, a very interesting phenomenon will happen, appear in this case. All right, some of them you come, so this is a homework 3, I will post on the blackboard, you can also check over there. Due on next Wednesday, next week, so you have 1 more week, 2 days to do that.